Yeah, let us now understand mass, spring, damper system. If I draw a typical diagram, which most of the textbook you will find, this is damper and this is the stiffness. Somewhere I am measuring x of t, and we understand x of t means we are talking about the displacement of perturbation about the equilibrium. The perturbation about the equilibrium, the extension of the mass when I give a disturbance through ft, and I am measuring x with respect to the equilibrium, right? And if I write the equations, I can easily show that f of t minus kx minus cx dot is equal to m d square x by dt square, right? Because if I am stretching the mass like this, there will be force kx, there will be force cx dot. I am assuming linear damping. So naturally, net force will be ft minus this. That will give us a resultant acceleration m d square x by dt square. No issues, Newton's law. Okay. This I can write it like this: m d square x by dt square plus c dx by dt plus k x is equal to f of t. Please understand this x there also, x is also identically, I need to write as x of t, because we are talking about response, right? These are perturbed quantities. We are trying to model its variation with respect to time. And this I can write in other notation: x double dot plus c by m x dot plus k by m x is equal to f of t by m. This is a very popular equation which you know how to solve it. Once you identify the type of differential equation it is, we have decided that since we are talking about dynamic stability, please do not forget we are talking about its response once the disturbance is withdrawn, right? And that is, in technical term, we talk about free response. That is, f of t is 0. So then, for free response, this, if you want to really understand it, it's like a spring. You have stretch it and leave it. Now there is no force. Leave it and see how it is moving. So this motion we are talking about free response. For an airplane, I have given elevator input and withdrawn. So I see how the airplane is moving. That is the free response. Okay. So we are focusing on the free response. So I can write this as x double dot plus c by m x dot plus k by m x is equal to 0, where I understand x is nothing but x of time. And this is free response. We will be analyzing controlled response also. That is, we will not take the elevator to a null position again. We will hold the elevator and see how finally it is going. But we are talking about free response because for the linear system, if I know the free response, I know how it is behave in a controlled response. For a mathematical understanding, you know that for a complete solution of a differential equation, it is a combination of complementary solution and the particular integral solution. So that comes from the control part. So we are talking about free response. Okay. If I do this, now you know for this sort of a differential equation, x equal to e to the power lambda t is a possible solution and if I put it here, I get lambda square plus c by m lambda plus k by m equal to 0. What you have done? Find from x, you find x double dot. X double dot will be nothing but, first x dot you find, x dot will be a lambda e to the power lambda t, then x double dot will be a lambda square e to the power lambda t, and this expression for x, x dot, x double dot, when I substitute here, I get a characteristic equation of this form where lambda is the, or lambda are the roots of this characteristic equation. You very well know that if lambda is positive, then this x will diverge. This x will go on increasing. To ensure that it decays, then lambda has to be negative. Okay? But you never know what is the nature of lambda. It could be positive, it could be complex, it could be negative. So who decides that? That is decided by the root of this equation, and directly you will see that value of c and m, k, they will decide whether lambda is pure negative or a complex number or a pure positive number. So what is the message? Message is, if you want to decide a particular type of transient, which is through x of t here, you can easily design the system such a way you get the desired lambda through selecting proper value of c, m, and k. Right? Okay? If this understanding is clear, so let us see what to do next. You could easily find out, you have seen the root as minus c by 2m plus minus under root c by 2m square minus k by m, which equivalently I can write lambda 1, 2 as minus c plus minus under root c square minus 4mk by 2m. They are equivalent. I will be using this form because I will be able to extract some important understanding from here. Okay? Now see the interesting thing. We have understood, since the solution of the perturbed quantity x of t is modeled as a e to the power lambda t, so how the x of t will vary will depend upon the nature of lambda. And lambda will have different values depending upon, number one, it has 3 roots. There are 3 values of lambda possible. One is if c square is less than 4mk. You could see from here, if c square is less than 4mk, that means this will be, the term inside the under root will be negative. Okay? So this is called a typical case. We'll be talking about under damping. We'll show why it is under damping. Or we say damping is relatively less. See, c square is a characteristic of damping, right? So c square less than this, you say in relative sense it's not much, damping is not much, right? Then it's possible c square less than 4mk, and it will be termed as under damped case or under damping case. Okay? Second possibility is there, that c square greater than 4mk. The same understanding here. Now we know damping must be pretty large. Okay? Think of a situation. Suppose if we take a mass spring shocker system, right? Mass spring, and there is air around that. So that there will be friction, and some energy will be lost through air friction. It will have some damping. But if I replace the air by water or oil, the damping will become large, or C value will increase. So it will be referred to as larger damping compared to only having air. Clear? So from that engineering sense, please understand when I talk about under damping and over damping. So this is C very large, relatively. And I have explained to you what is the meaning of that, very large. So it is an over damping case. And third one, obviously, comes to your mind, you're all mathematician, when it's a C squared equal to 4mk. And we'll be referring this as critical damping. One thing should be very clear at this point. If the C is less than C corresponding to critical damping, then it will go to underdamped. If C of the system is more than the critical damping C, it will go to overdamped. Is this clear? I repeat, if the C of the system is more than the critical damping, then it is a overdamped case. If C of the system is less than the critical damping, then it is a underdamped case. This much engineering understanding you must have. Then naturally question comes to your mind, what is critical damping? We'll discuss that. But mathematically, these three things should be clear. Please also understand one thing. When we wrote equation like this, mx double dot plus cx dot plus k of x equal to f of t, there was an implicit assumption that m, c, k all are greater than 0. Right? If c is 0, that means there are no damping. But there are positive numbers. They satisfy these conditions. Now, ask yourself honestly, whenever you talk about mass spring damper system, what comes to your mind? You think it must be oscillating and doing like this, right? But is this always true? Question is this. That means if I ask a question, once a system has mass spring damper system, or a system can be modeled as a mass spring damper system, does that mean it will be always having oscillations? That is a question you are going to ask and analyze from here. Second thing, please understand, the damping is not always at some part of a system which is separate from the main system. If there is a mass spring system, there is the air, automatic damping will be there. Okay? So don't think there is some sort of a, it's a modeling approach. Okay? We create a system for enhancing the damping by putting a fluid and allow the fluid to pass through an orifice. All such things we do. But normal spring mass system will have a natural damping because it is in a medium. Okay, right? So these two understandings were required. And now we would like to check whether a mass spring damper system necessarily means it will be always oscillatory system. So let us take the first case, under damping. What is this case under damping? That is the case c square less than 4mk. So the roots of the equation, if you recall, lambda 1, 2, we wrote as minus c plus minus under root c square minus 4mk by 2m. So once I say c square less than 4mk, that means this argument under the square root is negative, so it will give a complex number. Right? Okay. The moment it's a complex number, so I write, for notation, I write omega d is equal to under root c square minus 4mk, I put this value, by 2m, and you will understand why this algebra I am doing. So the characteristic roots then become lambda 1, lambda 2 can easily be written as minus c by 2m, which is nothing extraordinary I am doing. I am only substituting this expression here, and this will give me I, a complex number, unity WD. You could see here, this term is nothing but here. I have taken minus 1 root. So I is here. This is the generalized root, where you will find WD will be termed as damped frequency. We will talk about those. Don't get mixed up at this stage. And if you have revised your little bit of differential equation understanding, you can easily write x of t as c1 e to the power minus c by 2m t. Let me write this. Don't get unnecessarily disturbed. This expression, of course, never look very elegant, but we have no shortcut. We'll try to get the best out of it. Or x of t I can write as a e to the power minus c by 2mt cos of because you know, if these are the roots, one is minus c by 2m plus I omega d, and there is minus c by 2m minus I omega d, they are complex numbers. So there will be oscillations as far as modeling is concerned. And you could see the final solution is sum of two solutions. They are the basic solution. It is a sinusoidal part, right? But try to understand this. You do not require more than this mathematics to understand. One Laplace transform will require, which is also very simple for our purpose. So these are all 12 standard things. So do not get nauseated, what this expression is coming. Understand this. What is this expression telling you? It tells you x of t, there is a perturbed quantity, will vary with e to the power c by 2mt minus sine and cos function. So it is oscillatory like this. What is c? C is the damping constant. So if c is 0, there is no damping, how this solution will look like? It will be a sinusoidal, a cos function, right? If c is 0, this man becomes 1, so the amplitude will go on oscillatory motion with a sinusoidal form, right? There won't be any decay in the amplitude. Will there be? No. So no damping, so dynamically it is neutrally stable. That means what is the message? If you want to make a system dynamically stable, ensure that C is non-zero. Second thing message is, if you want highly damped, increase the value of C. Clear? This is clear? Okay. Now, we are discussing about underdamping case, so I continue here. I take this as x of t equal to a e to the power minus c by 2mt into cos of omega d plus phi, plus minus phi, whatever, it doesn't matter. You know that if c is 0, it is sinusoidal. If c is small, relatively, it will have oscillation, oscillatory motion. You see that? Oscillatory motion, because e to the power this is negative, the amplitude will go on decreasing. That is the important thing. Okay? And this e to the power minus c by 2mt, that is actually the damping contribution, which will, although if c was 0, it would motion like this. With small t, what will happen? C or small c damping, what will happen? It will start, the amplitude will go on decreasing, and it will come back to the equilibrium. So it's if c is small, and that is typically a case of underdamping case. So what you understood? Underdamping case, that is c square less than 4mk, there will be oscillations, and it will be underdamped, and it will come back to the equilibrium, right? But there will be oscillations. But please understand, we will not call omega d as a real frequency, we call it a pseudo frequency. Pseudo frequency. For simple reason, the term frequency, we'll call omega d as pseudo frequency, because generally frequency, when we talk about a periodic function. But strictly speaking, this is not periodic, although oscillatory, not periodic. So we use omega d, the expression which I have earlier given you in the beginning. And if I want to write that for your clarification, omega d we defined as under root c square minus 4 mk mod by 2m this is the damped frequency. This is the damped frequency. With the caution that we are very well aware when you define frequency, you talk about a periodic function. However, this is not periodic, although there are oscillations. Right? Okay. This is just for your information to be more precise.